Are we a go? Okay, so let me just introduce you and I'll move on the audio for you. Anyway, so welcome back everyone from lunch. I hope you're all well fed and with a lot of energy to go. So it's my pleasure to introduce Darren Croton. He'll be, as you know, he'll be talking through the video here. He's that little face in the screen up there. So just to give you an idea of Darren's way through astronomy, he did his Bachelor in Science with honors at Australia National University. Later, he got his PhD magna cum laude at the MPA in Garching, Germany. He was working with Simon White, is that correct? Can you hear me, Darren?
Yeah, I'm good.
Okay, so then he was a postdoc at Berkeley for about 3 years before he got his position at Swinburne University in Australia. That's where he's working now. He's been there since 2008, and he's been a full professor in Swinburne since 2015 for the last 2 years or so. So Darren is an expert mostly on simulations of galaxy formation and galaxy evolution. So he's going to talk a lot about how we simulate the formation and evolution of galaxies throughout the history of the universe using supercomputers and body simulations and semi-analytic models. During the course of his career, he's published over 100 papers with a combined citation of over 13,000 citations. He's mostly known in the community for his Croton et al. 2006 paper, at least that's the one I know the best, in which he introduced the idea of a different mode of quasar feedback, the radial mode of quasar feedback that regulates how gas accretes into galaxies later on after the quasar phase. And that paper alone has over 2,000 citations, so it's a seminal paper in the field of galaxy formation. More recently, he's the leader of the Theoretical Astrophysical Observatory project, in which the idea is that you can get data from get data from the simulations, simulate the observations of that artificial universe in your preferred telescope. So you can get all the simulated data as if you were observing with a real telescope and see what kind of data you would expect from that simulation. And that's a project that has been funded for $1.7 million so far. So it's a major project, and it could potentially help a lot what you're doing and what we're doing as well. So without further ado, let me pass on the word to Darren. So Darren, you have the floor for the next hour or so.
Wow, so thank you very much. I hope I'm coming through loud and clear. Let me just say, if there are any technical problems, please let me know, because there's nothing worse than talking away and nobody can understand you. And as someone who lived in Germany for 3 years and never spoke the language, I know how that feels. Let me apologize. I wish I was there with you guys. I was so excited to come down. I wanted to be there. I had lots of different things planned, which I can't do now. Unfortunately, I'm stuck in sunny California. Now, you know I'm in California because this is the size of the coffee that I'm drinking, okay? And I'll be continuing to sip on that. It's still morning here. Oh, I see someone's got Starbucks down in the front row. Well done. You're getting in the spirit. Okay, so I like being interrupted, but I may not know if you've interrupted me. So please, someone just throw something at the screen or whatever. If you have questions, you want some clarifications, just let me know, okay? I'm happy to stop. The whole point of this school is for you guys, not for me, okay? So before we start, I wanted to actually ask you some questions. I wanted to find out who was in the audience. So do we have any of the professors or faculty managed to stick around at this point?
Hi.
Can you guys stand up? I want to see how many of you there are. Yep, not many. Oh, yay, there you go. Good. Congratulations, guys. You made it. Everybody else in this room is aspiring to be like you. Okay. Postdocs. Postdocs, can you stand up? Any postdocs here? Stand up, guys. I see a hand. Stand up. All right. Let me say thank you. Okay. You guys do most of the science. Am I right? Am I right? You guys do all the hard work. You keep us publishing. Okay. We might get the money for you, but you guys do the actual hard work. So congratulations. And now all the students stand up. Yeah, most of you. Okay, good stuff. Let me just say, you guys are the future. All right? We're depending on you to get good and to do exciting science. There will be Nobel Prizes given in the next 10, 20, 30 years. Those prizes will be going to people like you. Okay? So work hard, but enjoy what you do and discover, okay? Because science is about discovery. I know you're going to stress over lots of stuff in your career, getting jobs and so on. If you want to know about that, just talk to the postdocs. They'll tell you all about it, okay? But don't forget to enjoy what you're doing, because you guys will be doing the discoveries that will paint what science looks like for the next 10, 20, 30 years. All right, so thank you for that. I wanted to see who I'm talking to. I hope you're enjoying the school so far. Let me just switch over now to my slides. Hopefully this will. All right, so how does that look? You can see my slide.
Yeah, this is perfect.
Yep. All right, good stuff. All right, so I was watching via YouTube yesterday, and actually learning a lot, especially about stellar population models. Let me just tell you, you never stop learning and you're always forgetting. So even for old people like me, and I feel old now, it's always good to be reminded of what you thought you knew. You realize you don't. What you're seeing in the background, and I hope this movie is coming through, is a hydrodynamic simulation of the formation of a spiral galaxy. Okay, so why would we want to do this? So let me just make a point about theory, because often in astronomy, and especially when you go to conferences, these two sides of astronomy often set up as opposing forces in some way, but they're not really, of course. So in other areas of physics, if you have a question, if you want to know something about the world, okay, you go to your laboratory. And you design an experiment, you put things in here, and you'll press this and electrocute that or whatever, and you'll get data back, and it'll test your ideas about what's happening, and from that you can make predictions and do further experiments in your laboratory. Now, in astronomy, we have no such laboratory. Okay? We can't take a star and put it into a lab in the basement of a building somewhere, or a black hole, or anything like that. We can't build, make a galaxy on the second floor of our new building, for example, like the plasma physicists or the nuclear physicists or the biologists or the chemists can do. For us, all we can do is point a telescope at the sky, a big bucket that collects photons, okay, and we record them. And that's all we can do, okay? And we do this at different wavelengths. We might do images, or we might take spectra. We might collect the photons for longer, but in the end, we're taking static pictures of our universe. And from that, we have to try and understand what's happening. And it's very, very difficult. So what's our laboratory? Our laboratory is the supercomputer. And this is why the role of theory is so important, because the theorists are really what are experimentalists in other sciences. In our supercomputers, we build the models, we run the simulations that allow us to do the experiments and tests to check if we actually understand what we're looking at when we look at things through our telescopes. And so looking at this hydrodynamic simulation up on the screen, we're testing our ideas of star formation and supernova feedback and hierarchical assembly and dark matter and gas physics and things like that. And it's probably true that we're going to get it totally wrong, or in part wrong. And that's because the universe is very complicated, and there's only so much detail that we can reproduce it at numerically inside a supercomputer. There are technical limitations. And so we have to know those. But just want to make the point. It's a very important point. The theorists use the supercomputers to test our ideas and our understanding of the universe. And in particular, we're going to talk about galaxy formation and supermassive black holes and things like that here. So I'll make this point a number of times through both my lectures, that don't be deceived, okay? What we're doing here is not creating the universe, okay? That's a really important point. And sometimes the movies that you see of simulations are so beautiful. They're more beautiful than the real universe. And we can get the impression sometimes that this is the real universe. It's not. It's a very imperfect representation, no matter how pretty we make it. Okay, so let's move on. So I have 2 lectures. I wish I had more. And I'm going to broadly split this into building synthetic universes. So synthetic universes are what I'm calling modeling the universe and the galaxies inside. And then the second lecture, I'm going to focus on how we might use those models and the data we generate with those simulations to try and understand the universe. And really, that's the most important part, because there's no point building a universe just for pretty pictures or to get more funding. Ultimately, the goal is to try and understand the universe. And this is where observers and theorists have to work together closely, and they're essential components of a broader process that is what we call astronomy. So in this lecture, I'm going to talk about the basics of how galaxies are built. And now I apologize in advance if for some of you this is really basic. Okay, let's strip it down. Sometimes I think we make things too complicated. Let's strip it down to the essential elements and see what we can get away with. And then we can add layers of complexity after that, depending on what we learn. Okay, we're going to talk about the difference between calibration of these models and their predictive power. And quite often we spend all our time on calibration and almost none of the time on prediction. And sometimes this is okay. Right? And I'll talk about that mostly in the second lecture, but we'll touch on that here. And I also want to discuss the uses and the limitations of these models, especially the limitations, because you have to know the limitations. When you write a paper, right, you're going to have a method section, you know, introduction and method section and a results section. For me, those sections are the easiest ones to write because I'm just stating factually what I found. The discussion section is the hardest one because that is about what it means. And really that's why you're doing it. And a big part of the discussion section should always be what the limitations were and what you can't say with what you've done. I always say to my first year physics students, and I know you've heard this a million times, but numbers are meaningless without error bars. And there are theoretical error bars on these models. We don't always put the error bars, or we do put the error bars onto the numbers we get out of the models when we apply statistics, for example. But just to the models themselves, there are uncertainties, significant uncertainties. We have to know those. All right, so one of the things that I wanted to do while I was there was have a little coding festival, basically. And so I'm going to put these up, and I haven't circulated them yet, but all my slides, I'll make sure all my slides get circulated to you so you can get these links yourself. Now, the galaxy model that I'm going to describe, or mostly describe today, or use as a framework to describe, is called the SAGE code. And it's freely available to use at this GitHub link. So if you want to download it and run it, be my guest. Let me know how you go. It should be really trivial and out of the box. If you also download these simulation tree files for the mini millennium, you should get a pretty good galaxy model at redshift 0. And now you're free to change the parameters, you're free to change the code, you're free to explore, do whatever you want. In particular, what I'll often do in a school like this is I'll set a challenge. So I'll talk a little bit about this later on, but this is the galaxy stellar mass function. And so on the y-axis here, we have the space density, the number density of galaxies as a function of, on the x-axis, their stellar mass. So it's basically a histogram of the abundance of galaxies. And there are 4 solid lines, and the black line is the present day, redshift 0. And you can see that this fits the data fairly well, right? The data is this, this dashed line, the black dashed line. And it misses a little bit at the massive end, but this is because the simulation is somewhat small, okay? And we're not getting enough massive galaxies in the box. When you go to the full millennium, it looks much better, right? So that's actually a calibration result, and I'll talk about this. This is not a prediction, this was a calibration. I made the model look like that. But if we look at these other lines, we're going to higher redshifts, so the galaxy population at higher redshifts. And you can see this is not calibrated. The model predicts that the mass function is different to what's observed, which are the dashed lines of the same color at redshift roughly 1.3, 2, and 3. And you can see that it doesn't do a very good job at all. It underpredicts the massive end and overpredicts the high mass end. Now, this is kind of a generic result for almost all semi-analytic models, all of these galaxy information models. And it's a real challenge. We understand why it does this. The universe is hierarchical. Little things grow into big things. And so at high redshift, you've got lots of little things. And that's why the stellar mass function is so high at high redshift, because there's so many little things. Unfortunately, in the real universe, we don't see that many little things. So there's something going on here. And because small structures grow into big structures at high redshift, there's not many big structures. And that's reflected in the model as well. Whereas in the universe, our real universe, there seems to be these big structures even at very high redshift. So it's weird, right? The model follows lambda CDM, which grows where structure grows hierarchically, and it behaves as we would expect. But the real universe seems to have this different behavior. And this is where dark matter and the baryonic growth decouple. And this is where the physics comes into play and what we need to try and understand. So the hierarchical growth of dark matter and the growth of structure, the structure of baryons, stars, gas, so on, they decouple at some point and they evolve differently. And we're not getting that correct in the model. So what I do in a school like this is I set you a task and I give you the code, and we have little workshops and tutorials where your job is to go and fix the model. Okay, easy, right? However, as an incentive, I throw money at you. All right, so I have prizes for the best fit and who can explain why the model fits so well, right? Or doesn't fit so well. So it really comes down to why this doesn't work or what you needed to do to make it work, all right? So unfortunately, we can't do that. So guys, you miss out on all that cash. But if anybody does want to download the code and have a go at this remotely, please do it. And I'm happy to, I'm really keen, excited actually to talk with you and work with you on it if you wanted to do it. But it's not something that I'll be able to lead you on because I'm not there, unfortunately. All right, let me take a sip of coffee. All right, so let's get started on some basics, what I call basics. And I hope this isn't too basic for you. Let's break the universe into 2 components. We'll break it into the skeleton and the flesh. And we're going to talk about these components separately. Now, the skeleton, of course, is the dark matter, and the flesh are the baryons. And we can break this apart, at least as a starting point, because dark matter dominates the mass of the universe. And so we can just worry about simulating the universe, simulating the dark matter universe as a starting point, and then later add the baryons on. Seems they're only a minor component, at least in terms of the large-scale growth of the universe. Now, this may not be a great way to model the universe. It may not be, but it's a starting point. And if it turns out that the models fail spectacularly, we have an opportunity then to go back and look at how to improve them. And it's that constant improving and examining. That's where we learn stuff. That's why we do the models. We don't do the models to make them right. We do them to learn stuff. And where they fail, that's often the most interesting use of them. All right, so initial conditions. Everybody loves initial conditions. Here are the initial conditions of the universe. And most of you would know that this is a map of the universe. This is the CMB. And these are temperature fluctuations, but they represent basically the density perturbations very early on. And from these density perturbations, large-scale structure ultimately grows. So we have an initial condition here, and we have our final conditions here. This is the 2DF Galaxy Redshift Survey, and this is the distribution of galaxies in the local universe on large scales again. So you can see that the CMB here, even though we've amplified the inhomogeneities, it's actually very, very smooth. The surface of last scattering is smoother than the surface of a billiard ball. Okay, so these slight overdensities and underdensities have been enhanced, I think, by a factor of 10 to the 5, just to see them. But in the local universe, we don't need to do any such enhancement. We see this cosmic web image. This is the large-scale distribution of galaxies. So we have our starting point and our ending point, and we build a cosmological model around that. And I'm not going to talk too much about the cosmological model itself, other than to say that the energy density of the universe is dominated by dark energy, as you know. But it's this dark matter for mass that we simulate with n-body simulations. And the 4% of atoms we're going to add later to our models once we've got the dark matter backbone. So we don't need this. Okay, here's the Hubble Space Telescope. So let's get rid of it. Okay, good. I like giving this talk, giving these slides at Space Sciences Telescope Institute, because many billions of dollars in careers have gone into Hubble, and then I destroy it. Right, we use one of these. Okay, so this is a supercomputer, and as I was saying before, this is your laboratory. For those who are the theorists in the audience, this is your lab, right? And this is where you guys will do your experiments. Okay, now I'm not sure how this movie is going to show up, but I think many of you might have seen a movie of a dark matter simulation. This is the large scale structure of the universe. So the overdensities, the bright overdensities are dark matter halos forming. Now, of course, there's no baryons here. So we've lit up the dark matter so we can see it, but you can see that the structure formation evolves with time. Gravity amplifies the dynamics of this dark matter that pulls it in to make these bound structures. Okay, and this is what we would want, because we know when we look at the universe that it's clumped and clustered, as I showed you in that 2DF Galaxy Redshift Survey slice through the actual galaxy distribution. All right, so what can we do with this? Now, one of the problems for modelers and simulators are that these simulations are getting insanely large now. Now that's fine for many science applications, but sometimes we really don't understand the physics well at all. And if we're going to spend a month, 3 months, 6 months of supercomputing time and generate 50 terabytes, 100 terabytes of data, we want more than one shot at it. If you get it wrong, you get the physics wrong. Let's say you're doing a hydrodynamic simulation where you're trying to simulate the baryons as well and all the hydrodynamics. If you get it wrong, you've lost that month, 3 months, 6 months, and 50 terabytes of data. You don't, well, I guess you could go and try and do it again, but then you're going to have to wait another month, 3 months, 6 months. We know how gravity works. So we just do the dark matter. We go into these simulations, which might have, nowadays they have up to 100 billion particles. So very large data sets. Even that's very hard to work with. So we find all the bound structures. So here's one dark matter halo in an n-body simulation. And you can see that well, the way we've found these is we find all the particles that are gravitationally bound to a center of mass. So that's it here. And we break it up into a smooth component and a clumpy component. Now, this smooth component would be what we call the primary dark matter halo. This is the main part of the halo. And the clumpy component is what we call the substructure. Now, these clumps are actually individual dark matter halos that fell into this larger object earlier in time. And if we're talking about our real universe, what we would have here is we would have a large galaxy at the center with all the satellite galaxies living in these clumps. Okay? Now, the good thing about this is that for the broad kind of galaxy modeling that we're going to do, we don't need to know where every one of those dark matter particles are in the simulation. Once we've found the halo, we can measure the mass of the halo by counting the number of dark matter particles. So in Millennium, for example, each particle was 8.6 times 10 to the 8 solar masses, inverse H. Okay? So a Milky Way sized halo would be, I don't know how many of those, 1,000, 10,000 particles would be defined by 10,000 particles. And we actually don't care where all those particles individually are. We just want their gross properties. So we can count the mass, we can count the velocity dispersion of the particles and just get a single number out for that. We can count the spin, we can measure the spin, so how the rotation of the halo, how the rotation measures in the halo. What else can we measure? Oh, the extent, so the radius, the size. And it's a reductionist problem. We can throw away those 10,000 particles now and just keep a few numbers which characterize the halo. Now, the beauty in this is that instead of having 20 terabytes of data to work with, now if we do this for every time step that we output, for every halo time steps found in the simulation, we bring this down to a couple of hundred gigabytes, right? So we've reduced the amount of data we've had to work with, which makes things much, much easier. Now, because we output the simulation at multiple time steps, we want to link halos across time steps. So for example, all the particles in this halo here, we would look in the next time step and ask, where are those particles? Now, most of them will probably still be in this bound structure, okay? But not all of them. That has interesting issues with itself. But generally speaking, we'll build up what we call a merger tree, and that characterizes how a halo grows and changes over time. And so all we need to do now for our properties of each halo is add a few pointers, these, so to link them across the time steps. So we can find the same halo in earlier times and build up the merging tree. So here, if we look back in time, we're going up here, there's a big halo down the bottom, and these dots would represent galaxies. We'll talk about galaxies in a minute. And you can see that at an earlier time here, this halo was 2 halos that merged during the time step. And if we go back, you can see it breaks into these smaller chunks. And this is just hierarchical structure formation in lambda CDM. Okay? Do we have any questions about that? Nope. All right, let's keep going. So these merger trees can be drawn many ways, just as an illustration. Here we've flipped it over, so time is now going from high redshift on the right to low redshift on the left. So I've got redshift 6 up here at the top and redshift 0 on the left at the top. And I'm showing you an example of a merger tree from an n-body simulation for a cluster and a Milky Way. And clusters are much more massive at redshift 0. And so they're made up of a lot more individual parts. And so at any given time step, let's just take this slice here. So this, these numbers in the middle would be the expansion factor, where 1 is the present day. So you can see that these circles also represent the mass of that bit of the halo at that time step. So some are big, most are small, and they merge and grow into this structure, which at redshift 0 is a single object. Milky Way type halo is built from fewer substructures as time goes by, but still, almost, I don't know of any halo almost that just grows purely without any merging at all. Even the ones that are out in the very underdense regions of the universe undergo some growth and merging. All right. Now, with this slide here, I want to make the point that the cosmology matters. So I haven't really talked about cosmology, and I just threw lambda CDM at you, and that is this top panel here, across here, lambda CDM, and there are 3 different redshifts, redshift 3, redshift 1, and redshift 0 on the right. And it's just a slice through an n-body simulation. But it's easy to take for granted now that we know the real universe is lambda CDM, and forget that there was a time when we didn't know what the cosmology was. And that wasn't actually that long ago. In the 90s, and that's when this figure is from, they didn't know that lambda CDM was the correct cosmology. So rather than just running one n-body simulation of lambda CDM, which is what we mostly do now, they would run multiple simulations of different cosmological models. And they would ask the question, broadly speaking, which ones are consistent with the observations? And you can see just a standard cold dark matter. So there's no dark energy in this second line, okay? That at any given time, redshift 3, redshift 1, or redshift 0, the structure formation is very, very different. The universe grew very different. So this tau cold dark matter, this is like a hot cold dark matter. So there's 2 species of dark matter particles, and one has a lot of thermal velocity and one doesn't. One's very cold. Again, the evolution of structure is different. And at the bottom, we have an open cold dark matter, so an open universe. So not only do these universes evolve differently, but if we just compare them at an individual time, like the present day, you can see that what you end up with can look very different. And so this is one of the ways that we can have confidence that the universe we live in is a lambda CDM universe. It's not just, oh, because Planck or WMAP said so. There are multiple channels of verification of this. And one of them is just to run that cosmological model in a supercomputer and have a look at the large scale structure that comes out of that and the statistics, either in Fourier space or the clustering in configuration space, or many other ways. And you can look at this and just go and look at the large scale structure of the universe from galaxy surveys and find a one-to-one correspondence with lambda CDM. Okay, so the cosmology matters, and it's easy to forget that nowadays. And a lot of people, there are some problems. I won't talk about, for example, the missing satellite problem, small problems with small scale structure in particular, the core cusp problem and so on. There are problems that persist, and people are looking at modifying the cosmology to see if they can solve these problems. But at least on large scales, the universe has to look like lambda CDM because that's what it is. Lambda CDM is basically one big fitting function to the universe. And we're exploring interpretations of that. What does dark energy mean and things like that? Can we have a physical model that dark energy naturally comes out of? But at the moment, any such model will have to look like lambda CDM because the universe looks like lambda CDM. All righty. Let's look at the good stuff now, the flesh. And so I'm calling these interwoven analytic models of the physics of galaxy formation. So if you go out tonight to the bar and drink a lot, I want you, after a couple of shots, to try and say that 10 times fast, because even I just had trouble saying that. But the physics matters, okay? And it matters because this is what we see. This is what we see, or most of what we see, okay? Galaxies, why do we care, right? Unlike the dark matter, which for most part can be just modeled through linear equations, galaxies have highly nonlinear evolution. they're the home of what I call internal phenomena, and I'll talk about these. These are things like the physics of supermassive black holes and feedback and star formation, the metal production, and all the interesting stellar physics that you heard about yesterday, even globular clusters and things like that. But they're also shaped, heavily shaped by external influences. And so the universe is not static at all. It's insanely dynamic. And so as these halos come in and collide and grow and merge hierarchically, so do the galaxies. And this has a big impact as well. Right? So let me just step you through some of the reductionist ways that we can understand the different phenomena that we think are important for galaxy formation. So let me start with star formation. We know star formation happens because we go out during the day and we see the closest star to us shining in the sky. So we have at least one example of this. The rest of the stars we see in the sky are not just pinpricks like they thought many thousands of years ago in a veil of what was otherwise some brilliant light, but other stars. And there are billions of stars in our own galaxy, and there are billions of galaxies. So measuring the integrated star formation of a galaxy is a very important thing to know. And we do that, and we find these interesting correlations. Now, I doubt that you can read the axis labels here. And so let me tell you what they are. So on the y-axis down here, this is a result from Kennicott. We have the surface density of star formation measured in nearby galaxies. So you just look at a galaxy and you put an aperture down, and you count how many stars are forming, basically. You can do this from the spectrum. So that's the y-axis. And for the same galaxy, you measure the surface density of gas in that galaxy divided by the dynamical time, a dynamical time. And a dynamical time might be like how long it takes for the spiral galaxy to do one rotation. Okay, so a characteristic time scale. And if you plot the surface density of star formation against the surface density of gas divided by the dynamical time, you get this relationship. And this is called the Kennicott-Schmidt law. Now we can use this, right? Nothing in this law here or in this figure tells you how stars form. Nothing at all. But it's an empirically derived phenomenological relationship that is true regardless. And so when we build up our model of galaxy formation, we'll use this kind of information. Ideally, we want to arrive at the point where our galaxies spontaneously arise from first principles. But the time and mass scales and the spatial scales that we would need to resolve to do that are impossible to achieve at the moment. So we use these empirically derived or empirically observed laws. So here's one of the key ones, the Kennicott-Schmidt law. We also need supernova feedback. So as I'm sure Claudia discussed, and I saw as well in other lectures, it was mentioned that the most massive stars that formed explode on short time scales. Many of them for a long time, but most massive ones explode on short time scales. It happens often enough that you'll get these winds driven out of the galaxy. And this is very important because not only do these winds move mass, but they also transport energy. And understanding the energy budget of a galaxy gives you insight into understanding the evolution of the galaxy. So this is a beautiful image of M82. It's quite a famous one where you'll see the winds are color-coded by red. And notice that they're emanating mostly from the center here as they go out in this shell. Most of the star formation does occur in the center of, near the center of these spiral galaxies. And you can measure how much mass is coming off, being blown off a galaxy based on the winds that are there. And this plot up here, it's kind of an old one now. It's by Crystal Martin. And what it's showing is what's called the mass loading factor or the mass loss factor. It's dm/dt on the y-axis. So how much mass per unit time is being blown off the galaxy as a function of the circular velocity of the disk of the galaxy. So this x-axis is just basically a scale for the galaxy. You could put mass on that scale. You would get a similar plot. And unlike star formation, where you get this nice relation you really don't get any relation here. Actually, one of the important points in this figure, in this graph, is it's plotted in units of the star formation rate. So per mass of star formation, per mass of stars that form, what is the mass that gets blown off due to supernova from those stars? So 2 here would mean twice the mass of gas in the galaxy is getting blown off per unit of star formation. So for every 1 mass of star formation that forms, 2 masses of gas gets blown off. Okay, but there's no real correlation with the scale or the size of the galaxy. Okay, but again, that's information we might want to know, because if we're modeling galaxies and we're using the Kennecke-Schmidt law to try and estimate how many stars are forming, we also want to model the supernova winds. And so we can use the star formation rate here and an assumption about how many, what this mass loading factor would be as a function of the circular velocity of the galaxy in order to build our model. All right, I showed you before all the subhalos and substructures. So we see these in galaxies, in galaxy groups and clusters, for example. And we also see the gas in those satellites being stripped off as they move through the denser medium of a cluster or even group environment. And this is one example of a satellite galaxy here, and the gas being stripped off as it moves through the hot intracluster medium. And we see this in multiple wavelengths. So we can now have special physics that reproduces the observations or mimics the observations we're observing in satellite galaxies that are unique to satellite galaxies. All right, so there's morphological evolution. So galaxies, halos collide, and hence galaxies collide and merge. And this would take, for example, 2 spiral galaxies that are merging here, and maybe multiple spiral galaxies, as seen here in this image, and takes them and randomizes the orbits of the stars due to the violence of the collision to produce elliptical galaxies. So in our model, if we want to understand the morphology of galaxies and how that evolves, we will tie that to the evolution of the dark matter and when mergers happen, and hence consequences of those dark matter mergers, which would be galaxy mergers. And we can update the morphology based on some simple assumptions based on what we actually observe. All right, so we know that there are black holes in the universe, and there are in particular supermassive black holes. We now have observations of the disks around them, but we don't even need that to see them. We can see jets. I'll show you that in a minute. Some beautiful results in the last 10, 15 years will show that there's a correlation between the mass of a black hole and the mass of a bulge. And that's plotted here. On the y-axis is the black hole mass, and on the x-axis is the bulge mass for a sample of, I think there's 30 or 40 galaxies here. And again, there's this nice correlation. And so we can use that if we're transforming the morphologies of our galaxies, so transforming disks into bulges using the mergers that would happen as a result of the merging of dark matter halos, we can infer a black hole mass given the mass of the bulge, the mass of the stars that turn into the bulge. We can infer a black hole mass in our model. And we might want to tie some consequences to that. For example, we might want to model the jets of AGN. And again, like supernova feedback, these jets will do work on the gas around the galaxy and perhaps modify the evolution of that gas, which would modify the evolution of the star formation, for example. And we see these bubbles. This is a nice plot of a cluster. So very large scale here, a cluster of galaxies. And in the center, there's a massive elliptical galaxy with jets emanating out. And you see these jets in the radio blowing bubbles in the hot X-ray emitting gas, which is the color behind. Okay, so on this side here, you'll see the 2 jets, one coming out this way and one coming out that way, and the X-ray gas is behind. And these cavities are now being observed quite regularly. So again, very broad picture. We haven't said how this happens, the details of it, just broad picture of what's going on. We want to know that because ultimately we want to model all these processes at sufficient level of detail to be able to reproduce something like this. And this is the diversity of the galaxies in the universe. And some will be beautiful spiral galaxies, edge-on blue disks. Some will have these rings, if you can see my pointer here, with very red cores. And then you'll get red spirals. You'll get these car wrecks over here, these mergers. And if I can find a nice big, I don't think I can find a nice big elliptical galaxy. Well, here's some elliptical galaxies up in the top left corner. So we want to have a galaxy model that gives us the broad properties of the galaxy population. And so what we do is we take all this phenomenology and we build a schema for how this might happen. And so I've listed here a lot of the processes we just discussed. I've broken the baryonic component of the galaxy population into different reservoirs. So stars, gas in the disk, which would be cold, gas in the halo, which would be hot, gas that gets ejected, black holes, for example. And then the lines that connect to these reservoirs, this is where the physics is. But we're not modeling this from first principles. We can't do that. We don't know how it works from first principles. So we'll use these observed phenomenological laws to do that. So the Kennickett-Schmidt law that I showed you, the dependence of star formation on supernova winds, the gas stripping, morphological transformation, and so on and so forth. And in particular, AGN feedback is a new thing that we've added. Okay, so this is going to be our analytic model. And basically, I'll come back to this. Oh, actually, I'll mention it now. So because we don't understand the details, we're not doing this from first principles. We don't have a Maxwell's equations for galaxy evolution, okay? So the relative efficiencies of these different processes are actually unknown. We can measure the Schmidt law, but we're only really measuring it in the local universe for spirals of a particular mass and so on. And there are issues there. So we parameterize these different processes, and this allows us to control the relative efficiencies of them. Now, it's important that those parameters be reasonable, at least for what they're meant to describe. So for example, we might have a parameter for the star formation efficiency. And a fiducial value might be set at 5%, okay? And observationally, I think it's like 3%, so it's close enough. If we needed a number there that was, 3, then probably our star formation efficiency parameter is not describing the physics that we're intending it to describe, and we need to go back and revisit that. And so we'll have a parameter for the star formation efficiency for supernova, so the mass loading, and some energetics there. So this is in the SAGE model for the different feedback mechanisms from AGN, so supermassive black holes, so the radio mode, low luminosity mode feedback, and quasar mode feedback, the growth during mergers and so on. How gas gets reincorporated after it gets blown out due to supernova or AGN and so on. And so we'll have these parameters, and these are really our mechanisms, our controls over how the galaxy population will evolve. And we want to set them for reasonable values, but because we don't know what these actual numbers are in detail across all of cosmic time, okay, we have to have some freedom to control them. But note though, that they're highly intertwined. So we can't just arbitrarily keep adding parameters. I like to, some people say with these models, oh, if you add more parameters, you can fit anything. And if only that was true. It's not true at all. It's like adding more steering wheels to a car. Okay? How well do you think you'd be able to drive here if you had 3 steering wheels and 3 different people controlling that steering wheel, right? At some point it gets harder. And these parameters and the efficiencies, the goal really is to reduce them down to the minimum number of independent parameters that you can. And so here's a slice through an n-body simulation, very large scales, 125 megaparsecs, and we'll run the flow chart, the schema that I just showed you on that. And that's as described in the SAGE model that you can download. And we'll add galaxies here. So this is the galaxy light that would be produced from a model that's described by that SAGE model. And I've color-coded the light from each galaxy based on the luminosity in different filters, so the actual color of the galaxy. And I'm hoping that the contrast on your projector there will be able to reveal this. But if I just have a look at the dark matter, so see this big hole here? There's an underdensity of dark matter here, but inside there's some structure. There's some dark substructure. But if we look at the galaxy population that's predicted in that environment, okay, it's mostly devoid. And so even though the baryons follow the dark matter and galaxies are grown inside halos, it's not a one-to-one correspondence, which is good because that's what happens in the real universe. And this is because there's a decoupling of the growth of halos and the growth of baryons. And any model should reflect that. So we can zoom in on a region here of the model. So here's a big cluster, and the galaxies are color-coded against the gray background, which is the dark matter, by its B minus V colors. And in the center, we have some massive galaxies, and as you move further out, the galaxies become bluer. And this is, again, how the real universe looks. And so our galaxy model is doing what we want. It's producing these broad properties of the galaxies, which we can then compare to observations. All right? So just to remind you that what we've done here are two kinds of simulations. We've done a numerical simulation of the dark matter. This is called an n-body simulation. And we've done an analytic simulation of the baryons. And we've coupled them together. Now, why would you want to do this? It's as I said before, that to do this with full hydrodynamics is very expensive. And you get one shot. You still have to set these parameters with a hydrodynamic simulation because you don't know the efficiency of star formation and you're not resolving the scales of star formation in a cosmological hydrodynamic simulation. So you still have to assume some parameterization of the physics. That's what we call subgrid physics. So there's a place for that, okay? But if you wanted to quickly explore the processes of galaxy formation, the relative importance of different processes and the efficiencies of such, you can build these analytic simulations. And as an example, this numerical simulation, the Millennium simulation, took a few months to run on a big supercomputer in Germany, in Munich. These analytic simulations I'm showing you, if anyone's downloaded it yet, on a laptop will take about a minute. Okay? So you can build your own universe with 100,000 galaxies with a Millennium simulation at mini Millennium simulation at redshift 0. And on a standard MacBook Pro laptop will take about a minute. Okay, an older laptop, 2 minutes. Who cares, right? It's not a month or 2 months, which is what you have to use with hydro simulations. So hydro simulations have their place. They're essential. And a lot of the physics, some of the physics that we would put into our analytic simulation here will have to be derived from hydro simulations. But if you want to quickly explore different physical ideas, these semi-analytic models are perfect for that. And they're wonderful at producing large-scale populations of galaxies. All right, so I said in the introduction, it's very important to understand the limitations of your model, and in particular, what's a result and what's a prediction. So nothing I've shown you so far is a prediction, and you should be impressed by none of it. Don't be impressed by any of it, because they're calibrations. And so let me show you some calibration plots. So what I mean when I say calibration is I sat there and I tuned the model, tuned the parameters, until I got a good match to a key set of observables. That's my starting point. There's an infinite number of bad models I could produce. So there's little value in just producing a bad model. I want a good starting point that I can use then to do some science with, that I can extend beyond. So here's one calibration plot. So this is the 2-point galaxy correlation function. This is the clustering of galaxies, basically the spatial distribution of galaxies in the Millennium simulation box. And you can see that the solid line is my model, and the data points are here from a galaxy survey. So I've calibrated to get a good spatial distribution. And here on the other side is the luminosity function of galaxies, like the mass function I showed you before, but luminosity instead. This is in the K band. And again, I've calibrated this to give a good match to the data. So just look at the solid line for a second. Okay, so I picked the parameters, which had to be reasonable and physically meaningful for what they're meant to do, but I picked them appropriately to give a good match to the data. Okay, and here is a color magnitude or color stellar mass diagram. So this is just a difference in two filters, V minus V against stellar mass. And you can see that this is on the right-hand side is from Baldry et al. For the Sloan Digital Sky Survey. I've flipped the axes here, unfortunately, and it's R-band luminosity, not stellar mass on the x-axis. But you can see where we get the bimodality and we get the gradient approximately right and so on. So again, calibration plots. I spent a lot of time making these look nice. Okay, so why should you be impressed, right? You shouldn't be impressed, okay? Where we learn stuff in calibrating are in the physical consequences of what we need to do to calibrate them. So let me just show you here. On the left-hand side, we have the K-band luminosity function. So on the x-axis, it's the K-band luminosity, where the further left is brighter, and the y-axis is the space density per unit magnitude. And the solid line here, this line that goes through the data points, is just the line I showed you before. So that's the calibrated line. If I turn off all feedback processes in the model, so with a switch, and I can do this in my universe. When you build your own universes, you are the God, right? You can do whatever you want, and you can explore and examine. So in my universe, I turn off supernova feedback. Stars, yeah, they might explode, but they don't do any feedback on the gas. Turn that off, and I turn off AGN feedback. I actually also turn off reionization as well, but I haven't talked about that. So turn off these feedback processes so the gas is not thrown out when stars form or when AGN go off. Okay, and I run the model, and that's what this other solid line does. Okay, and so that's the difference in the galaxy population, in the luminosity distribution of the galaxy population without feedback processes. And so what do we learn from that? Okay, there are two different mechanisms that are doing feedback here, and it turns out that at the low mass or the faint end, the supernova are what's important. It's this supernova that takes this line here of high abundance and flattens it to be closer to what's observed. Okay, at the bright end or at the massive end, it's the AGN feedback. It's the radio mode AGN feedback, and I'll talk a little bit more about that in a minute. It takes this heavily over-predicted line by many orders of magnitude, and it makes them much, much brighter. Basically moves this line back to where the data is. Now, why doesn't AGN work here at the faint end? Okay, you don't have enough supermassive black holes in these low mass galaxies. So AGN actually is operating in the model. It's just, it's not efficient at all because the black holes are either non-existent or way too small. It's only when you get into these very massive galaxies that are heavily bulge dominated or elliptical that the black holes get large enough, the jets get energetic enough that you can blow the gas out of the deep potential wells. Okay. Conversely, why isn't supernova acting efficiently at this high mass end? And that's because the potential wells are too deep. Okay. These massive galaxies live at the centers of very massive halos. And when the halos are so massive, you need a lot of energy to get out. Per unit supernovae, there's not enough energy. There's a point where the collective supernovae energy is not enough. And that point actually is at the near of the luminosity function here. That's where supernovas stop becoming efficient. So in the model, the AGN is actually implemented in proportion to the black hole mass and sigma cubed, so the velocity dispersion cubed, okay? And the supernova is put in proportional to the star formation rate from the observations, okay? And what that does, so these are based on observations, but what it does is it limits their effect to different regions of the histories of particular galaxies. And that's the physical consequences of doing this and why we can match these observables with these different physical implementations. Okay. So let's just say something about the limitations of the model. So this is very important. All right. So this is a slide I love to give. I haven't given this slide in a while. Let me take another coffee. All right. Alien invasion. All right, so look out, okay? Aliens are invading. And Karen is the leader of this alien force. Okay? she doesn't know much about the population down on Earth. However, her job is to go and conquer, okay, as you would want to do down there in Rio, conquer Earth, right? And you have this fleet of your spaceships. Okay, now, unfortunately, your commander comes to you and says, comes to Karen and says, look, we don't know much about these humans. You have to tell us something about humans before we go down. We might just get decimated. They might be too powerful for us. Give us some information. So Karen goes away and says, okay, well, let me build a model of humans. Okay, so let me just start. I'll build a model. Okay, so what's my model? Let me start. Let me approximate a human as round. And in some parts of the world, that's a pretty good approximation, unfortunately, especially up here in California. All right. Okay, so I'm going to approximate them as round, but there's some variations in that. Or maybe I'll account for those variations with a parameter. Okay, but that parameter has limitations, so maybe a distribution of parameters, say. What else do I know about it? Well, I'll approximate, their height and their shape. So humans might be, 180 centimeters on average. Okay, that's reasonable. They're not like 15 meters or 5 millimeters, for example. They could be. There are a lot of things on this planet that are 5 millimeters tall, but not humans, and humans are our subjects. So we have a rough shape, a rough height. We know the density and pressure on Earth, but that varies. It varies a lot, all right, depending on where you are on Earth. But we have a rough range for that, and we can get an estimate. Okay, and what about gravity? I know the strength of gravity, the acceleration due to gravity on the surface of the Earth. And so Karen starts building up a model of the human population. And with that model, she'll be able to make some predictions. Maybe the minimum and maximum flexibility of humans, right? How fast they can run, how fast they can move, how high they could jump, right? Very broad things that the commander of the alien invasion fleet might want to know, okay? How fast they can move, how high they can jump. Can they fly? Can they not fly? All these sorts of things, okay? And Karen builds this model. Now, this model will not tell you how the human eye works, right? Very important. It won't tell you how the human eye works. But for the alien invasion fleet, it tells you enough to get the job done, to learn something so you know what to expect. And so the models are only as good as the questions that we ask. So to use these models effectively, you have to ask the right questions. You can't ask questions that are so complex, the answers would be so complex that the model's not fit to give you those answers, okay? But it's also important to remember that for systems with infinite levels of complexity, and humans are one example, and galaxies are another example, the model will never, ever be correct, ever. So don't pretend it's correct. And when you see results at a conference that someone puts up and it looks wonderful, right? And I've been guilty of this as well. All the lines go through the data points and people cheer and pat you on the back, and there's little streamers that go off when your talk finishes, and dancing girls come out and so on. It's wonderful, right? Because you did so well, right? It's an illusion. The model will never be correct, and these are just models, okay? The point of these models are to learn about galaxy evolution, to understand the real universe, the observations. And it's always critical to keep that in mind, especially when you're writing your discussion section of your paper. All right. So let me finish up this lecture. So in the next lecture, I'm going to come back and I'm going to show you some examples of this, what I feel like are good examples of how to use models, and some examples where you can't use models. Okay, I'm not going to go and rip into anyone in the literature and sort of tear apart their paper and say, what a rubbish paper, how could you have done this? I'm not going to do that. I'm just going to show you what I think are some good uses of the models, where we actually learned some stuff we didn't know before, okay, about the universe using such models, okay, and how you, maybe, hopefully to give you some ideas of how you could use the models as well. Okay, but first, I talked about limitations at the start. Let me just highlight some of them. All right, semi-analytics, these galaxy formation models, they mostly assume that the cosmology is correct. Okay, we run the n-body simulation. We run it, we use it as if it is the God-given correct representation of the universe. Now, it might not be correct. The real universe might be warm dark matter, or it might be F of R gravity, or it might be something else. And if that's the case, all the limitations, all the incorrectness between the real universe or the real accurate model of the universe and lambda CDM, right, is not going to be accounted for in our model. And we might find that we have to do weird things to compensate in our model to get some observable to come out, when actually it's not the model that needs to be tweaked at all or adjusted, it's the cosmology. So we assume the cosmology is correct. And one of the fun things about these models is that you can change the input simulation on the same model and have a look at the difference. So you can test this and see the consequences, which is nice. We never used to be able to do this. Simulations used to be so expensive to run that there was basically one, and you would just use it and spend half your career just working with that simulation. I mean, how many papers out there are there using the Millennium Simulation, for example? In today's day and age, there's no excuse for that, right? We should be running a model on as many simulations as we can get our hands on to test the diversity of the predictions, that not just how the model works, but how the simulations change those predictions. All right, we also assume that these local correlations extend to higher redshift. Where we have higher redshift correlations, we will use them. But the high redshift universe is the frontier. It's the frontier. And anyone in the audience here who's working on high redshift observations, if I had a hat, I would take it off to you. This is hard stuff, okay? And don't let anyone criticize your work. It's hard. You guys are working at the frontier, okay, with very little data, crappy data. You could go into banking and earn a lot of money because the data's crappy in banking as well. And you have to make sense of crappy data. You guys at high redshift are doing that hard. So to model the high redshift universe, we often just have to make an assumption that the Kennickett-Schmidt law, for example, is also true at redshift 6. I think it might be true at redshift 6. Some observations tend to confirm it at least out to higher redshifts than 0. But we can't really do any better. The nice thing about the models is if we suspect that there's a problem with this assumption, we can change it. So we can easily go into the line of our code that says the star formation rate is equal to the mass of cold gas or surface density of cold gas divided by the dynamical time, blah, 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 with an efficiency. And we can change that correlation as a function of redshift if we wanted to test those ideas. Maybe we're having problems matching a particular observation. We find that if we tweak the star formation law a little bit, we get a much better fit. Then there's a prediction, right? We want to find something unique about that prediction, not just that it fits some high redshift observation, something unique about it that the observers can then go back and test that idea. Okay, and this is one way that I'll talk about tomorrow that you can use these models. All right, here's another important one, that the baryon fraction is universal. So if I have a dark matter halo mass, I said I have these different baryonic reservoirs. How do I know analytically how many baryons are in each halo? And we just use the baryon fraction. Okay, so 15% of the dark matter mass is going to be in form of baryons. Okay, we assume that that's true at all times, in all bound structures, in all environments, all the time. It might be at high redshift that that's only true out to twice the virial radius, or it's a function of mass or something like that. Universally, we can measure the baryon fraction, but on a halo by halo basis, is it true? Is it true in every environment at all time? Okay, it's a hard one to know, but we assume it in these semi-analytics. And again, you can test changing that assumption and see what it does for your model galaxy population. And we also assume that the halo properties predominantly determine the galaxy properties. So the mass of gas in a halo comes from the baryon fraction times the dark matter halo mass. The dark matter halo mass characterizes the potential well into which those baryons would fall. So it's a reasonable assumption to make. But it may be that there is decoupling of the baryons and the dark matter in particular ways where it's not the halo mass or the halo properties that determine some of the galaxy properties, but something else, right, that we don't know. These models just assume this, right? And others. So you have to keep this stuff in mind, because if your conclusions from your models depend on something here, you have to say. You have to say in your paper, and you have to understand what consequences that would be if it was different. Okay? It's very, very important to be honest with your results and not to get too excited. Okay, so they depend on that, but they're also at the mercy of the initial mass function, and I think Claudia talked about that yesterday. So basically the mass, the birth mass distribution of stars, or the way I like to describe the initial mass function, if you go down the hospital and you stand in the ward where babies are born, and you just record the masses of every baby that's born, okay? Other than getting arrested, if you did this for too long, you would eventually build up a histogram of the weight. That's the initial mass function of humans. Okay, so initial mass function of stars is the same thing. Okay, we assume that. Okay, and again, we can change that assumption, but basically this comes from areas of physics that we don't attempt to model in any detail, and in particular stellar population models. And one of my regrets of not being down there is I really, really wanted to talk to Claudia about stellar population models, because so much of the stuff we do depends on that, and we just have to almost blindly assume it and really try not to overinterpret our results wherever they come close to sensitive issues with the stellar population models. We're also at the mercy of the quality of the constraining observations. So I said that we calibrate the models, but what if the observations we calibrate against are wrong? Okay? Observers never like to admit when they're wrong. Am I right, observers? Right? You're listening to this nodding. Okay? Sometimes they're wrong. There are biases, your errors are underestimated. As I said, it's tough. The real universe is hard, okay? And we're at the mercy of the quality of these constraining observations and the quality of the underlying simulations, okay? There are numerical issues with all simulations. And again, if your model is saying something that's close to a regime where you're reaching the technical limitations of the simulation, you have to understand that, and you have to say where that is and try and compensate for it. Use better simulation, or you just can't make the claims that you'd like to make, and so on. All right, and as I emphasized before, the exact values of the parameter choices are mostly meaningless, okay? They should be in a particular range, but don't get too excited about it. 5% star formation efficiency versus a 6% one or something. These parameters are chosen to calibrate the model, and they compensate for a whole lot of things. Not all of them are physical. All right, and I think with 10 minutes to go, I'm going to finish there and take some questions. In the next lecture, I'm going to show you some results. As I said, show you some different applications for void galaxies, and what else do I have? Some environment stuff, some black hole bulge stuff, evolution of the black hole bulge relation, some different things that these models can be used for, where I think they were really useful in highlighting something that wasn't otherwise intuitively obvious. And we learned stuff, and I think these are good uses for the model. So I hope to lay some of that out for you tomorrow and sort of set you on the right path. But in the meantime, that's my last slide. In the meantime, the code is there. I'll send the slides so you can get that link if you didn't get it before. The code is there for you to use if you want to download it. If you have a laptop or go back to your computer, please share your experiences with me and share your model with me. And if you want to undertake the challenge that I set out, let me just go back to that. Here, you won't get that. I'm sorry, guys. I don't have cash to throw at you. If I was there, I would be showering it from above right now, but I don't. But if you want to understand and have a go at this challenge, send me an email, right? I'll help you, right? This is fun stuff. Okay, and if you want to use these models, please go ahead. There's the link. And with that, I'll finish and I'll take any questions that you might have.
So do we have any questions in the audience?
Hi. Could you discuss the missing satellite problem?
Can you repeat the question?
The missing satellites problem.
Okay. So the missing satellite problem is based on the observation that when we look out in the real universe, we see a particular abundance of satellites for a given halo mass, let's say. And let's define halo mass based on the mass of the most massive galaxy at the center. So for the Milky Way, we would look out and we would see these Magellanic clouds and maybe some dwarf galaxies a bit further away and so on. So that's fine. The Milky Way's halo is about 10 to the 12 solar masses, and the Milky Way is 5 times 10 to the 10 solar masses. When you go into a n-body simulation and you look at 10 to the 12 solar mass halos, you don't just find sort of 2 Magellanic-sized halos as subhalos in there. You find 40 or 20, all right? You find a lot more. And lambda CDM seems to predict a lot more substructure than what we can infer just from the satellite population of galaxies in the universe. And so there's a couple of solutions to this, right? One of them is to say, well, lambda CDM is wrong, okay? A natural consequence of lambda CDM is a lot of substructure, and that's wrong. And actually, it's not lambda CDM, it's a warm dark matter model. And the difference between a cold dark matter model and a warm dark matter model, so let me describe it this way. Cold dark matter has, by definition, has no or very little thermal energy. So the particles are just moving along, and where there's a potential well, they can easily get captured. Now, if you give those particles some thermal energy, if the potential is only kind of a bit shallow, the particles can escape because they have some thermal energy. Think of a gas, okay? And it's only when the potential gets really deep that the gravity is strong enough that thermal energy of the particles can't escape anymore. And so what this does is that it sets a mass scale below which structure won't form, okay? Because the potentials are too shallow and the dark matter has too much energy. So that's warm dark matter. And so when you give it some energy, these lower mass structures don't form, or they don't form as many. And that solves the missing satellite problem, because if you get rid of all these low mass substructures, because the dark matter can only really collapse into these bigger structures, if you get rid of these low mass substructures, you don't have the low mass satellites. And then you go and count the number of satellites in a warm dark matter simulation, and it's much closer to what you observe. So that's one solution. But unfortunately, warm dark matter fails in many other ways as a cosmology. And the ways that it fails far outweighs the ways that it helps. And so we tend to still favor lambda CDM. The other solution to the missing satellite problem is to say, oh, it's not the cosmology, but it's the baryonic physics. So yeah, these substructures, they form, these little ones, and they form in large abundance, but galaxy formation never really takes off in them. So the potentials are too shallow and the supernova is too energetic, and it just blows the gas out before you have a chance to form very many stars. And so there are lots of substructures out there, the correct amount in the real universe, as what lambda CDM predicts, but you just don't have galaxies or stars in them, and hence you don't have the satellites either. And so that's the missing satellite problem that they're missing from the simulations, and two solutions for that. And we really don't know what the answer is yet, whether it's the baryonic physics in the supernova and other mechanisms, preheating, reionization can help, or is it a change to the cosmology that's needed?
About the semi-analytics assumptions, two of them I'm not very comfortable. The local correlations extend to high redshifts, and the halo properties determining galaxy properties. It's just we have for now, or we have what's the main justifications for that?
So if I understand your question, you're uncomfortable with extending these local correlations out to high redshift, and what's the prospect for doing better? Is that right? Yep. I'm just as uncomfortable as you are. All right. But we can't do any better. We have to work with what we have. And until we can build galaxies from first principles, from Maxwell's equations, for example, or whatever, which I don't think we'll ever be able to do, we have to rely on the observations and maybe more sophisticated simulation methodologies in order to infer what these correlations might be. I agree, it's not ideal. As the observations get better at high redshift, we'll measure more statistics and identify new correlations and verify existing correlations or not, and we use them. So it's getting better. When I started this, most of these correlations were only really measured at redshift 0. And now pretty much most of the important ones, at least are measured out to redshift 0.5 or redshift 1. For some people in the audience, that may not seem like very high redshift. And it's not really, but redshift 1 is half the age of the universe. It's 7 billion years ago. So it's still a lot of cosmic time. And some of these correlations and statistics are being measured out to redshift 6, like the UV luminosity function, for example. So it's getting better, and we use what we can get access to. And I think this just underlines the importance of observers and theorists and modelers working together and not working independently. And so teams, theorists on teams, if you're a theorist or a modeler or a simulator, or that's what you want to do, you're in the audience, go get yourself on a team. It's great for your career. It's great for your publication record. And it's great for your science. And in particular, it's good for the observers because they need you there. They desperately need you, okay? And you need them.
More questions? Actually, so I have one, Darren. When I was a PhD student, I heard a lot already about the Millennium simulation. Nowadays, I hear a lot about Illustris and Eagle mostly. Can you talk a little bit how things have evolved since then and the main difference?
We've come a long way, a long way. Illustris and Eagle, the philosophy there was to run a lot of smaller simulations and calibrate the subgrid physics of the hydro. So for those who don't know, Millennium is an n-body simulation, so only dark matter, whereas Illustris and Eagle are hydrodynamic simulations. So they try and do the full hydrodynamic modeling. But they're still, and what's new about them is that it's a cosmological volume. And by cosmological, it's still much smaller than you would run an n-body simulation. So I think like we're talking 80 or 100 megaparsec on a side box, which is large but still small, whereas Millennium was 500 megaparsec on a box. And many of the simulations we want to run are gigaparsec cube. And remember, every time you double the box length, the volume goes up by a factor of 8. So going from 100 megaparsecs up to 1,000 megaparsecs is a massive increase in volume. So these are still small, even though they're cosmological. The way they ran them is they tuned the subgrid physics with smaller simulations and then progressively went up to their largest simulation boxes. So what you see as Eagle or Illustris is just the tip of an iceberg, a very large iceberg that they had run a lot of. There's still a lot of places they fail, and they have the disadvantage that they can't really run them again to try and understand the circumstances around where they fail. You don't often see where those failures are, of course, or the successes get presented in conferences, which is how scientists tend to work. We feel better about ourselves, I guess. And I'm not meaning to put down those simulations. They are almighty achievements. There's a new generation of both Eagle and Illustris being proposed, and I think they might even have started running some of them. And again, they're just pushing things back. So just like high redshift, where they're at a frontier, there's a frontier with these hydrodynamic simulations, and they're continuing to push them. But they're very much limited by the supercomputing technology and storage and memory and things like that. So things have come a long way.
Hello, he actually asked exactly what I was going to ask. So, but I still have another 2 questions, if I may. You were talking about the missing satellite problems, and you suggested as a solution that isolated dark matter halos without baryonic matter could be a solution to this. Is that the only solution that has been suggested so far?
Well, the two main solutions, I think, are in changing the cosmology or changing the baryonic physics. Now, there might be a problem with baryonic physics because, so at the moment I'm actually at UC Irvine, and James Bullock is here. And he has done a lot of work with the observations of low mass dwarf galaxies and looking at the velocity dispersions in the centers of those. And it turns out that just fixing the missing satellite problem with baryonic physics gives you the incorrect velocity dispersions in the centers compared to what we observe. And those velocity dispersions have to be set by the dark matter halo properties, or more by the dark matter halo properties. So it suggests that, their work I think suggests that it might be a change in the cosmology that's required, or at least a subtle adjustment to lambda CDM on these scales.
Okay.
And that's an important addition. It's on these scales. We don't have to throw lambda CDM out, but like most of physics, as our observations get better, we find more discrepancies, and our theories have to deepen to account for those changes. We don't throw everything out. We didn't throw Newtonian gravity out when we learned general relativity. General relativity encapsulates Newtonian gravity as a subset, and it's the same thing. Whatever the real cosmology of the universe is, lambda CDM is going to look a lot like lambda CDM. It'll just have these refinements which account for the differences that at the moment we struggle to observe. So I don't know if you have any other solutions that you have in mind, but primarily these are the range of solutions that people try to consider.
Okay. So actually saying that the missing satellites would be completely dark doesn't actually fix the problem. It raises other problems, from what I understood.
Potentially, like most fixes. Most solutions create new problems. And our jobs as scientists is maybe, it's like coding, right? You fix one bug and another bug pops up. And your job as a coder is to, fix all the bugs so that they stop popping up. And it's the same as scientists. And this is why what I like to emphasize is sometimes the solution is actually very complicated and contrived. That's definitely a true statement. The universe is complex, right? But ideally what you're looking for is a very natural solution. Something that comes out naturally from very intuitive principles about the universe that flow on from what you already know. And when we get into these cycles of more contrived solutions for problems, I always get a little bit worried, It's like epicycles, where there's actually a more natural solution that we're just not ready to understand yet. And this is why I wanted to emphasize at the start for you students there, is that you guys will be the ones really that are pushing these things forward. I think sometimes you get locked into a way of thinking, as try as you might, it takes fresh minds to come through and see things a little bit differently. And missing satellite problem is not the only problem like that. And if you notice in the literature, we don't talk that much about missing satellite problem anymore. People are just assuming that it's going to fix itself at some point. So I think it definitely highlights a deeper problem that has a natural solution that we're just not aware of yet. So, and I think it's potentially tied to the issue that I showed before with the mass functions, with the models. So there's this problem with the mass functions at high redshift with the models that basically just follow from lambda CDM, this overabundance of low mass objects and underabundance of high mass objects at high redshift. And again, I think there will be a natural solution that will solve this once we change something in our underlying assumptions, whether that's cosmology or methodology or something like that. And I have seen it happen before, and it's nice when it happens because you feel satisfied, natural solutions.
Okay, thank you. And the second question is actually just an observation. I don't know if the images were nearly identical or if it was my myopia, but the lambda CDM images, when you were comparing the models, the one for the z equal to 0, the 0 redshift, looked nearly identical to the open CDM image to me.
Let me go back to that. This one you're talking about?
Yes. To me, the present day lambda CDM looks identical to open CDM.
So definitely at redshift 3, structure is less evolved. Hopefully you can see that.
Yes, yes. In that redshift.
By redshift 1, there's more small-scale structure, I think, in lambda CDM than open CDM. So again, the evolution is slower, which is just a consequence of it being an open rather than flat universe. But the real way to see this is through the statistics, of course. I show this, especially with the cosmology, which is very well defined and can be simulated very precisely. The small differences in the statistics are actually meaningful. And so you would measure, for example, the power spectrum or the two-point correlation function or these sorts of statistics, and the differences would come out. But yeah, there is a similarity in the evolution. Both of them are cold dark matter. It's just basically the spatial structure of the universe here that's different, and you could probably find a redshift in lambda CDM which matched open cold dark matter. So redshift 3 wouldn't equal redshift 3, but perhaps redshift 3 and lambda CDM might match a different redshift in open cold dark matter. So.
Okay, thank you.
Yeah.
Do we have any more questions for Darren? So if not, let's thank the speaker again.
Thank you, guys.
So, and thank you very much, Darren, for being here with us virtually. We'll see you tomorrow. We have a coffee break now. I don't know if you have any announcements to make. Oh, sorry. Yes, there are posters presentations that were coming along. I'll leave Karim and Lohi for that.
So thank you very much, Darren. Now I'm gonna switch out here, but thank you very much, and we'll see you tomorrow. Thank you for a very nice talk.
Thanks, guys.
Bye.
Thank you.